All right, so we're going to talk about the mole today. Mole. All right, so when you think about the mole, a mole is analogous to a dozen in the sense that when you hear the word dozen, what number comes to mind? 12, right? When you hear the word mole, the number that should come to mind is 6.022 times 10 to the 23rd. It's a big number, right? It's actually up there on the wall back there. I used to have, half of it fell down. It said 1 mole equals, and then I had it all expanded so you could see all the zeros, and then it fell. I need to tape it back up there. But that's 602 sextillion is the number, in case you're curious. I'll tape it back up there so you can see all the zeros, right? 10 to the 23rd. And so this quantity is also called Avogadro's number. All right, so Avogadro's number is called 6.022 times 10 to the 23rd. What are some things that we would be able to count using moles? Would people work? There's 7 billion people on the planet. Billions 10 to the 9th. Would people be an appropriate thing to count with moles? Unless we're talking about every person who's ever existed ever, right? That probably wouldn't be a good thing to count with moles. What are some things to count with moles? Atoms, molecules, right? Atoms, molecules. What are some other things? Grains of sand on the seashore, right? Dust particles. Right? Why do we want to pick really, really, really tiny things? Because you have to have 6.022 times 10 to the 23rd of them just to have 1 mole. Right? So obviously people wouldn't work, cars wouldn't work, right? Books wouldn't work unless we're talking about letters in books, right? If we said how many letters are in every book that exists, well, that would be a good one to work with. But other than that, you know, it has to be something you've got a lot of, right? So that's why it's a good unit for counting atoms and molecules, grains of sand, particles of dust. And this number is derived from experiments involving gases. We're actually going to study gases later in this semester, and you'll see where Avogadro's number was derived from. And it gets the name Avogadro because Amedeo Avogadro is the person who's credited with making that discovery. All right, so we're going to do lots of calculations, and I've kind of boxed things off so you can keep everything organized. Let's first do calculations involving Avogadro's number. So this is when we calculate number of atoms or moles and going back and forth between these two. So let's look at this one. How many atoms are in a sample of aluminum that contains 2.5 moles of aluminum? All right, so we're going to make a conversion factor, just like we've always been doing. The unit you want to go away goes on the top or on the bottom? Bottom, right? The unit you want to get rid of always goes on the bottom, and then the unit you want to keep goes on the top. You multiply straight across and divide up, right? So we've got 2.5 moles. So 2.5 moles. MOL is just the shorthand, right? All right, we're converting 2 atoms from moles. So moles goes on the bottom, right? And atoms goes on top. So 1 mole contains how many atoms? 6.022 times 10 to the 23rd. Okay, so I multiply straight across and divide up. Now, let's refresh our memory on how to enter this exponent into your calculator. If you have a Texas Instruments calculator, you've got a button. I hope it's 2 uppercase E's. It might just be 1 uppercase E, depending on if you've got the big honkin' giant one or not. I think on the big, like TI 91s and stuff, it's just 1 E, maybe. I don't remember. It's going to be EE. Or you could have a 10 to the X button where you could put 1023. So you'd say 2.5 times, then you type 6.022, and then you hit EE 23, and that enters your exponent. And that tells your calculator 6.02 times 10 to the 23rd, and then hit enter. Now your calculator's dumb in the sense that it doesn't know anything about significant figures, right? Now this is a constant, which means it doesn't factor into our sig figs. We base our sig figs based on the number of sig figs we were given, okay? Not Avogadro's number. So we're going to round our final answer to how many significant figures? 2, right. So my calculator spits out 1.5055 times 10 to the 24th. I can only keep 2 sig figs, so that would be 1.5 times 10 to the 24th. Don't forget that exponent, right? Because there's a big difference between 1.5 and 1.5 times 10 to the 24th. And then my unit would be atoms. Do we see how to do that? Questions on how we did this problem? Set it up so that the unit you want to go away is on the bottom, the unit you want to keep is on the top. Anyone need help with your calculator? All right, let's do the next problem. All right, now we're going to go the other way. I give you atoms and convert that back to mole. How many moles of magnesium are in a beaker that contains 1.23 times 10 to the 23rd atoms? So take the number you begin with, 1.23. Okay, just FYI, I am going to do a shortcut. If you see me write uppercase E, that's just abbreviating this. That's like using the button on your calculator, okay? I get lazy. So when I write 1.23 E23, that means 1.23 times 10 to the 23rd. Okay, you can use this notation too, as just don't use lowercase e, because lowercase e is it's a number like pi. Okay, that's called Euler's number. Don't use lowercase e, because that implies that's like the same thing as writing pi. So it's a real number, right? It's just a symbol that represents it. Don't use lowercase e. All right, 1.23 times 10 to the 23rd atoms is what I have. Now I want to set up my conversion factor so that the unit I want to go away is on the bottom, the unit I want to keep is on the top. So where does atoms go? On the bottom or on the top? Bottom, right? Number associated with atoms goes with it. And we're converting to moles, so moles goes on top. 1 mole contains how many atoms? 6.022 times 10 to the 23rd. So atoms goes away, and my unit is now moles. So again, we type it into our calculator, 1.23 E23 divided by 6.022 E, oops, yeah, that's right, 23. All right. So my calculator doesn't know anything about sig figs. It's just going to give me an answer, 0.20425, blah, 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 blah. How many sig figs am I keeping? 3 sig figs, right? So my final answer would be 0.204. And what would my unit be? Moles. Always ask yourself this question. If you're calculating number of moles, you should not get some answer with a giant exponent times 10 to the 50th, right? That would not make sense. You should get a relatively small number, a number like, 0.5 or 1 or 10 or 3 or 0.001, right? Relatively small. If you get something with an exponent of times 10 to the 46th number of moles, you've got your conversion factor upside down, right? You should only get big, giant, huge exponents when you're calculating number of atoms or number of molecules. So always ask yourself if your answer makes sense. If you've got some huge, humongous exponent and it's going with number of moles, you've done something backwards. Likewise, if you're calculating number of atoms and you get 0.1, that doesn't make sense either, right? Because when you calculate number of atoms or number of molecules, you should get a gigantic answer. So take a minute and try these 2 problems. I'll pause the recording. Erase. Move the screen up. So you try these 2. A sample of calcium chloride contains 4.89 times 10 to the 22nd calcium chloride molecules. How many moles is this? If you add 0.5 moles of neon to a balloon, how many atoms are in the balloon? So take a second and try those, and we'll go over them. All right, let's go over these. Let me give myself some space here to write. Okay, A sample of calcium chloride contains 4.89 times 10 to the 22nd molecules. How many moles? So you say 4.89 times 10 to the 22nd molecules. All right, where's molecules going to go? On the bottom or on the top? Bottom, molecules. And then moles goes on top, right? 1 mole contains 6.022 times 10 to the 23rd molecules. So we don't really care what it is, right? I could say a sample of sand is 5 times 10 to the 30th, right? It doesn't matter what it is. So calcium chloride molecules is what we're working with. 4.89 times 10 to the 22nd divided by 6.022 times 10 to the 23rd. That gives me molecules cancels. My unit is now moles. 0.0812, blah, 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 blah. How many sig figs am I able to keep? 3 sig figs, right? Is this 0 right here a significant digit? This 0 right here? Think about it. Is this a measured value or is it a placeholder? This is just a placeholder, right? So these are my sig figs. So it'd be 0.812, 0.0812, sorry. 0.0812, and my unit would be mole. Okay, this is just a placeholder, and this is just a placeholder, because all this 0 here is telling you that the actual value doesn't begin until the 100th place. Okay, because you could just omit this and put an underscore there. Also ask yourself, if I write this in scientific notation, does this 0 go away? And the answer is yes, right? Because if you write this as 8.12 times 10 to the negative second, right? Notice that placeholder went away. So this is not a significant digit. It's not a measured value, it's just a placeholder. Zeros to the right of a non-zero digit would be significant though, right? If they are actually measured values. This is not a measured value. Do we see why this one doesn't count as one of our sig figs? All right, any questions on number 1? Good? All right, let's do number 2. And again, it doesn't matter what we're dealing with, calcium chloride molecules, particles of dust, hairs on someone's head, right? It doesn't matter what your unit is. As long as you understand how to set up the conversion factor, it'll work the same every time. All right, if you add 0.5 moles of neon to a balloon, how many atoms are in the balloon? So you take the number you're given. Now these zeros right here, are they significant or insignificant? There's a decimal, so are those zeros significant? Yes, they are. Those are actual measured values. So 0.500 moles times, where's moles going to go, bottom or top? On the bottom, right? So 1 mole contains 6.022 times 10 to the 23rd atoms. So moles cancels, you're left with atoms. So you say 0.5 times 6.022 times 10 to the 23rd. And your calculator is going to give you an answer with 4 sig figs. My calculator says 3.011 times 10 to the 23rd. But can I keep all of these sig figs? That's 4 sig figs, right? I can only keep 3, right? So that would be 3.01 times 10 to the 23rd, and my unit would be atoms. How do we feel about that one? Any questions on number 2? Okay. There will be questions on the next Mastering Chemistry homework about mole conversion, so I want to make sure we've done lots of examples. All right. Now here's a problem that we have. We can't see atoms and molecules. I mean, that's just not possible, right? We can't see them. They're beyond the scope of our vision, right? And even if I had unlimited time, if I had all the time in my entire life from the beginning of the point where I could count all the way till the day I dropped dead. If I used my entire lifespan, I would never, ever, ever be able to count to 6.022 times 10 to the 23rd. I would never be able to do it. You can go home today and start counting, and you can count until you're 100 years old. And trust me, you're not going to make it to 10 to the 23rd. That's sextillion. That's an enormous, mind-bogglingly huge number, right? You're never going to be able to count that high. So you can't see atoms in the first place. And even if you could see them, you could never count that high, right? You just couldn't do it. Go to the beach and start counting grains of sand. Like, that's what you're equivalent to doing. It would just never, ever work in your lifetime. So if I want exactly 1 mole, how would I actually measure that? How would I know that I actually have 10 to the 23rd and not 10 to the 24th, 10 to the 20th? Right? How would I actually know that I've got exactly the quantity that I want? And so the answer to my problem is called molar mass. The answer to my dilemma is molar mass. So by definition, every atom of any element, gold, argon, strontium, whatever element you pick, every atom of a given element is identical, right? So if I take a sample of gold from here, and then I go to California, take a sample of gold from there, and then go to Mexico and take a sample from gold there, right? No matter where I go, every atom of gold is going to be the same if it's gold. So if I know the mass of one atom of that element, then I can multiply by 6.022 times 10 to the 23rd to get the mass in grams of 1 mole. Does that make sense? And then I have a number that I can go to the balance and measure out. And then I would know for certain I've got 1 mole of that substance, right? It would be just like if I want a mole of jelly beans, right? Well, I can't count to a mole. I can't count 10 to the 23rd of jelly beans, right? That's something I can see. But if I know the mass of 1 jelly bean, and I multiply by 6.022 times 10 to the 23rd, I could get my dump truck to back up and do a scale, because it would take a dump truck to get a mole of jelly beans. It's going to be a lot, right? And I would know, okay, I've got exactly 6.022 times 10 to the 23rd jelly beans, assuming they're all identical. So the molar mass is the mass number from the periodic table. So if I want to know the molar mass of magnesium, I just look at the mass number. And refresh my memory, is the mass number the bigger number or the smaller number? The bigger number, right? It's the one that's a decimal. Because the mass number is the average atomic mass of all the isotopes, right? That's why that one is a non-whole number. So molar mass allows us to convert from what? It converts us from moles to mass in grams, and vice versa. If you've got mass in grams, you can convert that to moles. So molar mass is just the mass of 1 mole of that element. Do you understand why we need molar mass? Right? Because if I want exactly 1 mole, how do I have any certainty that I actually have 1 mole? Well, the only way to do that would be A, count, which I can't do, or B, come up with a workaround so that I can weigh it out and know exactly, hey, I've got that exact amount. And so, last thing here, the molar mass of a compound, all you do here is you add up all the molar masses of the atoms. So for instance, if I want the molar mass of water, there are 2 hydrogens and 1 oxygen. So it's 2 times the mass of hydrogen plus the mass of oxygen. And then there's my molar mass for water. Okay, molar mass has the units grams per mole. Those are the units for molar mass. because 1 mole has this mass in grams. Does this make sense? This is why you need your periodic table today. And obviously, I'll give you a periodic table on every test and quiz and all that good stuff. You're not going to be expected to commit mass numbers to memory. Although, after doing this enough times, you might start memorizing them, which is always fun, because then you can, drop that into conversation from time to time. You're out with your friends. Hey, did you know that the mass number of sodium is 22.99 grams per mole? And they'll just be so fascinated. Or they'll roll their eyes, one of the two. Probably the second one. All right. So let's do some conversions with molar mass. This is when we convert grams to moles and moles to grams. How many grams of iron should I measure out if I want 1.92 moles for an experiment? So let's just pretend I'm doing an experiment and I need 1.92 moles. Well, I can't go to my molometer. That doesn't exist. There's no such thing as a molometer. But I do have a balance. And that is something I can sit there and I can just put it out, wait till it says 1.92, and then I know. Right? Wrong. You got to count how many grams that is. Right? How many grams is that? Then I can go to this. So 1.92 moles. All right. 1 mole has the mass of how many grams? Look at your periodic table. 55.845. Does everyone see where this number came from? This is the mass number on the periodic table for iron. Now, don't round your mass number and go with your periodic table. So if your periodic table says 55.85, that's fine, okay? It just depends on the periodic table you're looking at. In the end, it's not going to make a difference because once you round, you can only keep 3 sig figs. Whether or not you have 55.85 here versus 55.845 here isn't going to make a difference because you're going to round your final answer anyway. Multiply straight across and divide up. So moles cancel, and I'm left with grams. So I say 1.92 times 55.845. My calculator spits out 107.2224. I can't keep all those sig figs. How many sig figs can I keep? How many sig figs am I given? 3. So how many so what should I round my final answer to? Just 107, right? And my unit would be grams. Just by the way, if you had 55.85, let's see what your answer would be. 1.92 times 55.85. That gives you 107.232, which still rounds to 107. Right? So on a test, you'll all be using the same periodic table, so it won't matter because you're all going to have the same molar mass to begin with. Any questions on how we convert moles to grams? Again, just ask yourself. You don't need to memorize a zillion rules. Just ask yourself, what am I trying to get rid of? And put it on the bottom. What am I trying to keep? Put it on the top. And then figure out what number goes with your corresponding units. And you'll be golden. All right, let's do the next one. Converting grams to moles. 21.82 grams of sodium reacted with water during an experiment. How many moles of sodium is this? All right, so we're starting with grams this time. 21.82 grams. And now we need to set up a conversion factor. What am I trying to get rid of? Grams. And I'm trying to keep moles. 1 mole has a mass of how many grams? What's the molar mass of sodium? 22.99. So I multiply straight across and divide up. So 21.82 divided by 22.99. This is going to be pretty close to 1 mole, right? 21.82 divided by 22.99 gives me 0.949108, blah, blah, blah. I can only keep 4 sig figs. Right, so that would be 0.9491, and my unit would be mole. Don't forget units. How do you feel about this one? So again, if the problem involves grams, if you see the word grams in your problem, you need to think molar mass. All right, that's the key word there. If you see number of atoms, number of particles, etc., you need to think Avogadro's number. Right? That's the biggest mistake students make, is using Avogadro's number in the wrong place or using molar mass in the wrong place. All right, here are 2 for you to try, and I will pause the recording. If you need 4.75 moles of methane, which has the formula CH4. What mass in grams is this? And a reaction produces 110.74 grams of carbon dioxide. How many moles is this? Take a second and try these. All right, let's go over these problems. We've got our methane. Methane's a gas at room temperature, so it's not like you could measure it out with your balance. You have to come up with an alternate way of doing that. You know, measure the container, turn on the valve, let it come in, measure it after the gas comes in. Right? That's a gas. But that's beside the point. You can still measure its mass in grams. 4.75 mole times. We want grams, so grams is on top, and 1 mole is on bottom. How do you get the molar mass of methane? Methane's not on the periodic table, so how do you get it? You got to calculate it, right? So that's 12.011 plus 4 times 1.008. So that's about 16, but let's be precise. 4 times 1.008 plus 12.011. I got 16.043. Do you agree? All right, so 16.043. So moles cancels. Well, that's not a straight line at all, is it? Times 4.75. All right, my calculator says 76.20425. I can't keep all those sig figs, so how do I round my final answer? What's my final answer? 76.2. Right. My units would be grams. Any questions on how we did that one? All right. Number 2. A reaction produces 110.74 grams of carbon dioxide. How many moles is this? So we have to convert grams to moles this time. 110.74 grams times 1 mole as a mass of whatever the molar mass is, right? So carbon dioxide is CO2, so that's 12.011 plus 2 times 15.999, or if you rounded that to 16, some periodic tables just have it listed as 16, which is also fine. So let's see, 2 times 15.999 plus 12.011, 44.009. So if you had rounded that to 16, your answer would just be ever so slightly different, right? But it's not going to matter in the final answer. Again, on tests and quizzes, we'll all have the same periodic table, so we don't have to worry about how many decimal places your periodic table carries out versus the person next to you. 110.74 divided by 44.009. Grams cancels, I'm left with moles. That gives me 2 points. I can only, I've got 5 sig figs to keep here, so 2.5163, right? 1, 2, 3, 4, 5, yep. And my unit would be moles. I have 5 sig figs to keep this time because I had 5 sig figs at the beginning. How do we feel on going that direction? Yes? This is all easy stuff, right? All right, let's now look at some problems that are two-step types of problems. Calculations with Avogadro's number and molar mass. So you're putting it together, right? These are, by definition, going to be two-step problems because you can't go straight from atoms to grams. There's no way you can do that because I don't have a conversion factor that allows me to go atoms. What is the mass of these number of atoms? I can't do that. I'd have to convert atoms to moles, then moles to grams, or vice versa. Grams to moles, then moles to atoms. So let's go this direction first. Converting number of atoms or molecules to grams. A beaker contains 2.9 times 10 to the 30th water molecules. What mass of water is this? So I can't do this all in one step, right? I have to go molecules to moles, and that's when I'm using Avogadro's number, right? And then I go moles to grams, and that's where I use molar mass. So let's start. 2.9 times 10 to the 30th molecules times 6.022 times 10 to the 23rd molecules per 1 mole. Right, that's step 1. So let's calculate that. Now we're going to carry extra decimal places. My final answer can only have 2 sig figs. But we want to carry extra digits and round at the very end to avoid having a rounding error, okay? Because we don't want to round at step 1 and then round again at step 2, because our answer will have too much rounding in it. So we'll carry out extra decimal places. 2.9 times 10 to the 30th divided by 6.022 times 10 to the 23rd gives me big number. 4, 8, 1, 5, 6, 7, 5. Well, that's a lot. And my answer here is moles. All right, now let's convert that to grams. 1 mole has a mass of what? Water's H2O. So this is 2 times 1.008 plus 15.999. And I think we already did this one on the previous page. Yep, 18.015. Okay, so times 18.015. That's still a big number. How many sig figs can we keep? We can keep 2. Running out of space. That's right here. Equals 8, 6. We can keep 2 sig figs. So 8.7. 8.7 times 10 to the 1, 2, 3, 4, 5, 6, 7. 10 to the 7 grams. Now, normally when you're calculating number of grams, it's not that big. We divide that by 1,000. That's 8.67 kilograms. And when you think about it in that unit, 8.67 kilograms of water is about 8.6 liters, which isn't that much, right? If you think about, this is 1 liter right here. So if you think of 8.5 of these, that's your mass of water. Right? Water's got a density of 1 gram per milliliter. So when you think about it that way, a swimming pool is still way, 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 way more grams than this. But nonetheless, when you're calculating grams, normally your answer doesn't come out that big. But when you're thinking about water molecules, you would normally have a big sample, right? If you're thinking about a swimming pool, or even that cup right there is going to be a big number. Do we have questions on how we did this one? Questions here? All right, let's go the other way. So I guess that wouldn't be beaker. It would be a drum. A beaker, 8.5 liter beaker is not really all that feasible. So maybe it would be a drum or tub or something like that. Beaker is probably not the best word choice there on my part. Okay, you have a 5-gram sample of ammonia. How many ammonia molecules do you have? So 5.0 grams. All right, we need molar mass. So ammonia, so this is 14 plus 3 times 1.008. And that's, for all intents and purposes, 17. If you really want to get particular about your decimal places, 3 times 1.008 plus 14. That gives you 17.024. So 5 divided by 17.024 gives me my answer in moles. So that's 0.2937. Let's just carry out extra decimal places. Moles. Now we need to convert moles to molecules. 1 mole contains 6.022 times 10 to the 23rd molecules. So take our answer times 6.022 e to the 23rd. And I'm keeping 2 sig figs. So that's 1.8 times 10 to the 23rd molecules. Is that a reasonable answer for number of molecules? Yes, that would be. How do we feel about this one? Am I going through it too quickly? All right. Let's look at the next part. All right, this is really important. Only use Avogadro's number when the problem asks for what? What are the key words to look for if you're using Avogadro's number? Molecules, number of atoms. Right? Something that you would need a big number, a big quantity. Only use molar mass when the problem asks for mass, right? In grams. And converting atoms to grams and grams to atoms is a 2-step problem. All right. I've seen several of you already working ahead on this, which is fine. Here are some practice problems that I want you to do. Move on to the next page because everything got kind of wonky here. And so what I'd like you to do is take a second and work on these problems. I'll pause the recording and then we'll go over the answers. Okay, so what I did is I just wrote out the answers and I scanned it, and so I figured we could go through it this way as opposed to me standing at the board going over every single one of these, because you may not need me to go over every single one of these. If you are okay, then I feel like that's a appropriate use of our time. What do you guys think? If you need me to actually work it out, I'll be happy to. So number 1 was a 2-step problem because it said how many atoms are in an adult human body. So there's part A, when we're converting moles to atoms. Now notice it says a typical adult contains about 30. There's no decimal place there, right? That's 30 with no decimal place. So that means it's only got 1 sig fig. If it was 30 with a decimal place, that would be 2 sig figs. But this is 30, no decimal place. So that means I have to, hold on, move that so I'm not, So that means that I have to use one significant figure, right? 30 moles, no decimal place, times Avogadro's number of atoms per mole. My calculator spits out 1.8 times 10 to the 25th, but I can only keep one significant figure. So that's why it's 2 times 10 to the 25th. Because 30 has no decimal place, so that's only one sig fig. Part B says, if a sample contains 1.00 times 10 to the 20th calcium atoms, how many moles are in the sample? All right, this one has 3 sig figs, so my final answer needs to have 3 sig figs as well. How do we feel about number 1, part A and part B? Any questions? Anyone need me to work it out? I'd be happy to work it out. All right, let's look at number 2 and 3. Okay, we'll fit there together. All right, in number 2, the question was, how many H2S molecules are in 3.8 moles? So we don't need Avogadro's number. I mean, we don't need molar mass here, right? Because we're asked how many molecules. So anytime you see the word molecules, you should think Avogadro's number, right? So 3.8 moles. 1 mole contains 6.022 times 10 to the 23rd molecules. I had 2 sig figs here, so I can keep 2 sig figs here. And again, don't forget this exponent. A lot of students will write 2.3. And there's a very, very big difference between 2.3 and 2.3 times 10 to the 24. So please don't forget this part. Right? It's written as that little tiny superscript in the top corner of your calculator, and sometimes it's easy to overlook it. So make sure you don't forget that exponent. Questions on number 2. All right, number 3 said, how many helium atoms are in 1.35 moles of helium? So again, the problem says atoms. Anytime you see the word atoms, that should immediately make you think Avogadro's number. 1.35 moles is what I begin with, and 1 mole contains Avogadro's number of atoms. I had 3 sig figs here, so my final answer needs 3 sig figs here. And again, when you're calculating number of molecules or number of atoms, you should have a big giant exponent, right? Always use that as a self-check. If you're calculating number of atoms and you get 0.009, that doesn't make sense, right? Because when you calculate number of atoms, it should be a gigantic exponent. Likewise, if you calculate number of moles and you get 10 to the 46th, you've got your conversion factor upside down. You multiplied where you should have divided. Okay, so always use your units as a self-check. A number of atoms, number of molecules, number of particles is going to be a huge giant number. Number of moles is not. Questions on number 2 or number 3? Everybody good? Am I going through these too quickly? All right. Let's look at number 4 and number 5. So number 4 said, how many grams of copper should I measure out if I want 3.5 moles for a reaction? So I don't have any way to measure out a mole, but I do have a way I can measure out grams, right? I just use my analytical balance. So 3.5 moles, 1 mole of copper has a mass of 63.546 grams. Where did I get this number? What's that? That's the mass number for the periodic table, right? And never round, carry out the number of decimal places that your periodic table has. So if yours was 63.55, your final answer is going to be the same. Because you round to 3 sig figs, it's going to end up being 222. Right? That's got 3 sig figs. My original had 3 sig figs. My units would be grams. Now that's something I can go to the balance and get my beaker and just add until it gets 222, right? And then I know, okay, I've got 3.5 moles. For number 5, the problem said, an experiment uses 4.89 moles of aluminum. What mass in grams is this? Okay, so 4.89 moles. 1 mole has a mass of 26.98 grams. Again, where's this number coming from? Periodic table, right? That's just the molar mass, which is the mass number. So I'm multiplying straight across and dividing. I forgot to cross out my units, right? I keep 3 significant figures because it had 3 significant figures initially, so that's 132 grams. Any questions on 5? If you made any mistakes, are you seeing where you're making them? Yes. All right. All right, here's 6. 6 is a 2-part problem because the problem says, how many carbon atoms are contained in a 25-gram sample? You can't go straight from grams to atoms, right? That's not something you're capable of doing. You go grams to moles and then moles to atoms, right? So I converted grams to moles. using the molar mass, right? It's 25 grams, and 1 mole has a mass of 12.011 grams. So I'm just dividing by the molar mass. Carry out extra decimal places. Then you take this number and use that as your starting place for your next step, converting moles to atoms. 1 mole contains 6.022 times 10 to the 23rd atoms. My final answer needs 4 sig figs because I had 4 sig figs initially. 10 to the 24th, is that a reasonable unit for number of atoms? Yes, it is. A lot of students either stop right here and say, there's my final answer, and they'll put molecules or atoms instead of, moles. But again, ask yourself, is 2 atoms reasonable? Would 2 atoms have a mass of 25 grams? Boy, I hope not, because we'd be a whole heck of a lot heavier if 1 atom weighed, if 2 atoms weighed 25 grams, right? That doesn't make sense. So make sure that your answer is reasonable. These are the kind of problems that get students into the most trouble, the 2-step problems. So always just ask yourself, where am I starting? Where do I need to be? And then what do I need to do to get there, right? Grams to moles, moles to atoms, atoms to moles, moles to grams, right? Those are the 2-step problems. Any questions on 6? Questions on 6? All right, let's look at 7. We'll put 8 up there too. Well, no, let's just do 7. 8's 2 steps. Okay, 7. How many moles of sodium are in 15.75 grams? Grams to moles, so that's just molar mass, right? Problem didn't say anything about particles or atoms or anything like that. So that's just straight up molar mass. So you say, okay, 15.75 grams. 1 mole has a mass of 22.99 grams. That's the molar mass from the periodic table, right? So multiply straight across and divide up. I had 4 sig figs here, so I need 4 sig figs here. My unit would be moles. Forgot to cross out my grams. How do we feel about number 7? If you made a mistake on any of these, are you seeing where you're making them? Yes, yes, yes. All right, number 8. Number 8 is a 2-step problem as well. The problem asks, if a balloon is inflated with 10.5 grams of helium, how many helium atoms are in the balloon? So not right off the bat, before I even pick up my calculator, I should ask myself, is this going to be a big number? The answer is yes, right? We're calculating number of atoms. So I shouldn't come up with 17. Maybe 17 times 10 to the 30th, but not just straight up 17. So 10.5 grams, I have to go grams to moles first, right? I can't go straight from grams to atoms. There's no conversion factor that would allow me to do that. So the molar mass of helium is 4.002 grams to moles. There's my number in moles. Then I'm just going to take that number and do a second conversion factor. Moles to atoms, right? So I take my answer, multiply by Avogadro's number. This is what my calculator spits out, 1.5799 times 10 to the 24th. I need 4 sig figs, so I need to round. So that's why it's 1.580 times 10 to the 24th. Questions on 8? How are we feeling about 8? Like I said, the 2-step problems are the ones that people get the most confused by, because you have to do grams to moles, then moles to atoms, or atoms to moles, then moles to grams. You have to go through the process twice. And if you're going through it twice, that's 2 opportunities to put your conversion factor upside down instead of 1. But always just check yourself and make sure, does your answer make sense in terms of your exponent? If you've got a humongous exponent and you're calculating number of atoms, that's fine. If you've got a humongous exponent and you're calculating grams, that's probably not fine. I mean, your exponent for number of grams shouldn't be anything bigger than like 10 to the 3rd, 10 to the 4th. We did 1 10 to the 7th, but we were calculating the mass of 8.5 liters of water. All right. And even then, that wasn't that high. All right, number 9. We got another 2-step problem. The problem says, how many molecules of calcium chloride are contained in a 14.1 gram sample? So I want number of molecules. I should have a big exponent. So first I convert grams to moles. How did I get this 110.978? Where'd that come from? Right, I have to add molar mass of calcium plus 2 times the molar mass of chlorine, right? And then that gives me 110.978. So grams to moles gives me moles. Now I say, okay, moles to molecules, use Avogadro's number. Final answer needs 3 sig figs because I had 3 sig figs initially. Remember, we don't use molar mass or Avogadro's number in terms, they don't factor in terms of sig figs. We're treating them like constants. We're only basing our sig figs off the number that we were given originally. How do we feel about 9? Questions on 9? All right, 10. 10 is an easier one. Calculate the number of moles of potassium bromide in a 0.515 gram sample. So this time it's not asking for molecules, it's just asking for moles. So if you got this one wrong because you didn't have the right formula, you need to go back and review formulas, right? Because if you didn't know the formula for potassium bromide, you obviously wouldn't have been able to come up with this molar mass, right? So make sure that if formula writing is what caused you to miss this problem, you go back and review your formulas. So grams to moles, molar mass is mass of bromine plus mass of potassium. 119, if you had just left that at 119, your final answer wouldn't have been that much different. Actually, it wouldn't have differed at all, really. We keep 3 sig figs. We got 0.00433. Rewrite that in scientific notation, 4.33 times 10 to the negative third, and my unit is moles. How do we feel about 10? Questions on 10. All right, the last one, number 11. Calculate the number of moles in a balloon that contains 6.89 times 10 to the 18th carbon dioxide molecules. So this is a 2-step problem. And you can do yours like this when you're ready. I just smashed it all together into one big problem. And if you understand doing it this way and it makes sense to you and it doesn't mess you up, more power to you. If you still want to do it as 2 steps, here's what that would look like. So if you're doing it as 2 steps, it would be 6.89 times 10 to the 18th molecules times 6.022 times 10 to the 23rd molecules in 1 mole. Right? So you're just stopping after step 1. So when you do it that way, you'd say 6.89 times 10 to the 18th divided by 6.022 times 10 to the 23rd. That gives us 1.144 times 10 to the negative 1, 2, 3, 4, 5, 50 moles. Now we just do our second conversion times 44.009 grams per mole. So times 44.009. We get 5.04 times 10 to the negative 4th grams. So if you want to do it like this, instead of one big giant one, that's fine. You just do this times this times this divided by this times this. You're going to get the same thing either way. So if it makes more sense to you to split it up as the 2 separate problems, please do it that way. Please. Don't unnecessarily confuse yourself. How do we feel about number 11? How do we feel about these kinds of problems as a whole? On the course website, if you go to the course website in the moles folder, and you go to the bottom of that folder, there is a page of practice problems with the answer key. Okay, so those are problems that I just made up myself, and I put the answer key at the end. So if you need more practice on this, those problems are there for you. And then also if you look in the syllabus, obviously there's alignment to the problems in the book. But if you want some of the ones that I've made, those are posted on the course website. All right, so that's where we're going to stop for today.